Hi everyone, I'm Stacey. About a year ago, I started using Twisted for a BitTorrent client that I was writing as a project at Hacker School. Then last summer, I worked full-time as a developer on Twisted and became a committer. So I've spent a lot of time trying to unravel Twisted, and I'm here to share what I've learned in this introduction. But before we get into what Twisted is, let's take a whirlwind tour of some of the things we can do with it. Twisted comes with a bunch of configurable servers, which can be run from the command line using the Twisty utility. All of these servers were written using the Twisted library itself. So here's the command to spin up a web server on port 8080, which serves static and dynamic content out of the current working directory. We could run a chat server, which authenticates users from the information in a file, or a name server, which uses information from a host file to translate domain names to IP addresses, or a secure shell server, which authenticates users with the SSH keys on the server. Or we could run a server which shares the files in the current directory. These are all examples of the kind of powerful applications that we can build ourselves with Twisted. Now let's go back to the beginning. Twisted is an event-driven networking engine in Python. We'll talk briefly about what that means. Then we'll cover Twisted's abstraction for event-driven programming and networking. We'll talk about Twisted's low-level and high-level APIs. And finally, we'll talk a little bit more about the capabilities that Twisted offers out of the box. Twisted is a library which provides building blocks for creating network applications. That is, programs that communicate with other computers over a network. Twisted makes it easy to write programs to talk to other computers using standard protocols, like HTTP for accessing web resources, TCP for transferring files, SMTP for sending mail, and many more. Twisted also provides tools that we can use to implement our own protocols. And it provides working implementations of clients and servers for many standard protocols. One of the notable characteristics of network communications is that when one computer sends a request to another, the response isn't available immediately because the messages have to travel back and forth across the network. Because of this characteristic, the event-driven style of program organization works really well for network applications. In an event-driven system, program flow is determined by external events. In Twisted's case, primarily network events. GUI programs use this style also, but the events are things like mouse clicks or button presses. To understand why event-driven programming works well for network applications, let's look at some alternate models first. Let's say we have three tasks that are independent of one another, perhaps fetching web pages from three different sites. In the single-threaded synchronous model, the processor runs one task at a time from beginning to end. Because it's synchronous, when a task needs to do a network operation, it has to wait till the result's available before it can move on. The gray areas here show the time the processor's waiting, which is known as blocking. This model isn't very time efficient. It would be really nice to use the processor to do other work while a task is blocked, but it's very easy to follow what's happening in the code. In the multi-threaded synchronous model, each task is assigned to its own thread and runs from beginning to end. The operating system is responsible for allocating processing time among the threads, possibly on multiple processors or interleaved on the same processor. This is much more time efficient because when one task blocks, other tasks can proceed. However, it's much more complex than the single-threaded model because control can switch between threads at any time. It makes it harder to reason about the program flow, and we have to take special care with shared resources so that they're not corrupted inadvertently. The event-driven model is single-threaded but asynchronous. Instead of blocking on a network operation as a task in a synchronous program would, a task in an asynchronous program yields other tasks while it waits for the network operation to complete. An event-driven program is organized around an event loop, which waits for events to occur and dispatches them to callback functions which have been registered to handle the events. The event-driven model displays the best characteristics of the other two. Like the single-threaded model, one task runs at a time, eliminating a lot of complexity. But like the multi-threaded model, it's time efficient. Now we'll take a look at the abstractions that Twisted offers to support event-driven programming. Twisted's event loop is called the reactor. That's because it reacts to events. It repeatedly waits for network and timer events to occur and invokes the callback which has been registered to handle each event. A callback is simply a method on a Python object. In Twisted, all code execution occurs as a result of either a network or a timer event. The reactor needs to use the functionality provided by the operating system to perform network communications and to efficiently detect events. From operating system to operating system, the APIs may vary, but Twisted provides a uniform interface and hides the differences by providing a variety of different reactor implementations. The interface for the reactor provides a way to start it, stop it, and schedule functions to run at a later time. For a server, we can tell the reactor to listen for various types of incoming connections, and for a client, we can tell it to initiate a connection to a server. The listen and connect functions set up callbacks to run when the connection's established. One thing to note is that once the reactor starts, it has total control of the program, and other codes only run in response to events. So before it started, we have to make sure to tell the reactor to listen for at least one event. Otherwise, it will run forever with no way to register any further callbacks. When an event occurs and a callback's invoked, control passes from the reactor to application code. And the application code will continue to run until it explicitly returns control to the reactor. That should happen when the task it's doing completes or if it needs to block on a network operation. Instead of blocking, the application code should register a callback with the reactor to be run when the operation completes, and then the application code should return control to the reactor. In reality, things are a little more complicated. We might want several things to happen when the operation completes, and we might want a separate callback to handle error conditions. Twisted provides a very nice abstraction for managing callbacks called a deferred. Deferreds are one of the more complicated parts of Twisted. I'm going to go over the basics, but don't worry if you don't catch all the details. They won't be necessary to understand the rest of the talk. So we can think of a deferred as having two chains of callbacks. One is used when an asynchronous operation completes successfully, and the other when an error occurs. Before I get into the details of deferreds, I'd like to go through an example of converting a piece of synchronous code into a piece of asynchronous code using a deferred. Here's the synchronous code. GetPageSync makes a network request for a web page and blocks until it receives the page or an error occurs. If the page is received successfully, it's passed to the translate function, and the result of that's passed to the display function. If an error occurs, the unavailable function is called. In both cases, the cleanup function runs last. In the asynchronous version, GetPageAsync initiates the request for a web page, but it doesn't block waiting for the result to come back. Instead, it immediately returns with a deferred, which will eventually be fired when the page is received or the operation fails. This deferred initially has two empty callback chains. And in the code here, we call functions on the deferred to add callbacks to the chains. When this code's done running, control returns to the reactor. And this diagram shows the callback chains that are set up by the asynchronous code. You can see that the flow of control is essentially the same as that of the synchronous code. On the success case, translate, display, and cleanup are all being called. The difference is that this code can run independent of when the request for the page was made. Here's a look at how the reactor interacts with the application code. In the synchronous case, there's only one call into the application code. After the call to GetPageSync, the red line shows the time that the processor's blocked before the page comes back, and the translate, display, and cleanup functions are run. In the asynchronous case, there are two calls into the application code. The first time, GetPageAsync is called, and the deferred is set up. Then, control returns to the reactor. The green line shows the time that the processor, that we're waiting for the page during which other processing can take place. Then, when the page comes back, the reactor fires the deferred, which transfers control back into the application code, and the translate, display, and cleanup functions run. Now back to the details of deferreds. We can think of deferred as having multiple levels, each with a callback and an errorback, although either one can be a pass-through. The deferreds interface has 4 functions which can be used to construct the callback chains. Each of the levels in this deferred was created by a different function, which is shown on the right. When the asynchronous event associated with the deferred occurs and the operation is successful, the first function in the callback chain is invoked and with the result of the operation. But if an error occurs, the first function in the back chain is invoked with the error. Program flow doesn't necessarily go straight down the chains. When an error occurs in either a callback or an back, the next call is to the back at the next level down. Similarly, if a callback or an back function completes without an error, its return value is passed to the callback at the next level down. This allows an back function to correct an error and allow normal processing to proceed. And it allows an error in a callback function to be handled by error processing code. That's all I have to say about deferreds. They're an important part of Twisted, but for the code we'll be looking at, Twisted uses them under the covers. As we move into the abstractions that Twisted uses for networking, let's first take a look at the networking model used in the internet. The Internet Protocol Suite consists of 4 layers of functionality. The 2 lowest, the link and network layers, are responsible for sending packets across the network. The transport layer is responsible for transmission of bytes between 2 peers. TCP is a connection-oriented transport layer protocol, which provides a reliable stream of bytes. UDP is an unreliable connectionless transport layer protocol. And SSL, or more properly TLS, provides an encrypted byte stream. The application layer provides meaning to the bytes that are being transmitted over the transport layer. Its protocols are used to provide user services over a network. In addition to HTTP, FTP, and SMTP, there's also POP and IMAP for retrieving mail, DNS for address resolution, IRC for chat, and a lot more. At the transport and application layers, we can think of there being a virtual connection between peers. At the transport layer, bytes are being exchanged, while at the application layer, higher level messages are being passed. Let's see how the 4-layer internet model maps into Twisted. Twisted relies on the operating system to provide link and network layer functionality, and it uses the sockets API for some transport layer functionality. But Twisted provides a transport abstraction which hides the details of sockets. The equivalent of the application layer in Twisted is called a protocol. The terminology here can get confusing, so I'll be careful to distinguish between application layer protocols and Twisted protocols. Twisted uses 3 basic abstractions for all of its networking. In Twisted, a transport represents one end of a connection between 2 endpoints, over which bytes can be sent and received. A Twisted protocol represents one end of an application layer protocol, which determines the format and the meaning of bytes that are sent and received over a transport. And a protocol factory is used to create the appropriate protocol when a new connection is established. It's needed to remember what type of protocol should be created in the time between when the reactor starts listening for connection requests or initiates a connection and when the connection is actually established. In Twisted, a protocol is always paired with a transport, but because they're distinct, it's very easy to mix and match them. HTTP usually runs over a TCP connection, but with Twisted, it's very easy to run it over SSL to provide HTTPS. Twisted also provides special transports for testing, which would be difficult to do over real network connections. This diagram shows the flow of information between the protocol, transport, reactor, and operating system. To send a message or drop a connection, a protocol calls a method on its transport. And a transport lets its protocol know when data has been received or the status of the connection's changed. The transport uses the underlying operating system sockets API for network communication, and it interacts with the reactor, which uses the poll or event notification API for detecting events. With an understanding of Twisted's networking abstractions, let's take a look at some examples which demonstrate the use of one of Twisted's low-level APIs. One of the most basic programs we can write with Twisted is an echo server. It accepts connections from clients and sends back an identical copy of the data it receives. This is the entire program for an echo server using Twisted. It consists of an echo server class, which is a protocol, and an echo server factory, which is a protocol factory. Before we start running the reactor, we tell it to listen for connection requests on port 8000 and give it an echo server factory to use to create an echo server protocol for each new connection. Then we start the reactor and wait for events. When a connection request is received, a new transport is created, and the build protocol method on the protocol factory for the listening port is called to create the appropriate type of protocol, in this case, an echo server protocol. Later on, when data is received by the echo server protocol, it simply writes the data back to its transport. Now, let's take a look at the corresponding echo client. The pattern is very similar to the echo server. It again consists of a protocol and a protocol factory. This time, to start the program, we tell the reactor to connect to a specific host and port, give it a factory which will create an echo client protocol when the connection is established. And then we kick off the reactor. The difference between the echo server and the echo client shows up in the protocol. In the server version, we use the default implementation of connection made, which is called right after a protocol is created. In the client version, we override this function to send a message to the server. Since we're talking to an echo server, we should get back the same message we sent. When we do, data receive will be called, and we'll print out the received message and then tell the transport to drop the connection. Notice that through the write functions on the transport and the data received function on the protocol, we have access to the stream of bytes being sent and received over the transport layer. Using this low-level API, we could develop our own twisted protocol, which implements an application layer protocol of our own design. We could also develop one which implements a standard application protocol. But the really nice thing is that we don't have to do that because Twisted has already developed a series of protocols which implement standard application layer protocols. And it provides high-level APIs for using them. Next, we'll take a look at one standard protocol and the API that Twisted provides to use it. SMTP stands for Simple Mail Transfer Protocol. It's a connection-oriented text-based protocol for sending email. Since it's text-based, we can use Telnet to connect to a mail server, send messages, and see the server's response. Each response from the server begins with a 3-digit code followed by text. In this Telnet session, we can see that once we've connected to the server, we receive a 220 response indicating that the server's ready. To start a mail session, we send a intentionally misspelled hello command, and the server replies with a 250 code, which means that everything's okay. To start sending an email, we send a mail from command, which includes the address of the email sender. Then we send at least one, but possibly multiple receipt to commands, which specify the intended recipients of the mail. Then we're ready to send the body of the message, which starts with a data command. The server sends a 354 reply, which means that it's waiting for the body of the message. Finally, we send the message itself, followed by a period. At this point, we could send another message by starting over with the mail from command, or we could terminate the session by typing quit. If we wanted to use Twisted to build an SMTP client to send out a set of messages, we could create a new Twisted protocol, probably organize it as a state machine, and it would initially send out a hello command, and then repeatedly cycle through the mail from, receipt to, and data commands to send out each mail message. It would need to parse each response from the server and handle error conditions. Twisted gives us all the tools to build an SMTP client. But the really great thing about Twisted is that it already includes an SMTP client that does almost all of that. In order to be general purpose, information about the messages to be sent have to be provided to Twisted's SMTP client. And Twisted offers an API for that purpose. For each piece of information that the SMTP client needs to send to the server, it calls an internal function to get the information. It repeatedly cycles through the calls to get mail from, get mail to, and get data until get mail from returns none, which means there are no more messages to send. And after each message is sent, the SMTP client calls the sent mail function. To use this API, we need to subclass SMTP client and override these functions to provide information about the messages we want to send. Let's use this API to build a client to send a single message to a mail server. We'll make our single message sender a subclass of SMTP client, which is itself a subclass of protocol. And we'll save the information about our message as instance variables. The underlying SMTP client takes care of constructing the SMTP messages and parsing the server responses. When it's time to send each piece of information about the mail message, the SMTP client gets it by calling the appropriate API function, which we've provided. After cycling through the 3 API functions one time, the SMTP client calls getMailFrom a second time to see if there's another message. And our getMail function returns none. GetMailFrom function returns none to say there are no more messages to send. Now let's use our single message client to send a single message to a mail server. To make things really easy, let's create a function which takes as parameters the address and port of a mail server, the 3 pieces of information about a message, and a reactor instance. It creates a single message sender factory, which I have not shown, and initiates a connection to the server. This is the same pattern that we saw in the Echo client. So let's add a bit of code to use our send message function. First, we'll define the body of the message. Then we'll call send message and tell it to connect to the server running on port 8025 of localhost and give it the sender and recipient addresses, the body of the message, and the reactor. Since we don't have a reactor running yet, we'll start one. But if we needed to send a message out as part of a larger event-driven program, we could pass in the reactor that was already running. In case you want to play around with this at home, you should know that the standard port for SMTP is port 25, but a lot of ISPs block it to prevent spam. So here we're sending to a server running locally on port 8025. In a minute, we'll see how to start up this server. What we just did was use Twisted's SMTP Client API to create a specialized client that sends one message. And we wrote a function to connect to a server and use that client to send a message. At this point, you may not be surprised that Twisted comes with this functionality included as well. The Twisted equivalents of our single message sender and single message sender factory are the SMTP sender and SMTP sender factory. Twisted also includes a version of the sendMail function, which can easily be used within larger event-driven programs to shoot off a message. SMTP has been superseded by another protocol, Extended SMTP, which offers, it's similar, but it offers authentication and other options. Twisted also provides eSMTP equivalents for all the SMTP classes. On the server side, Twisted provides implementations of SMTP and eSMTP servers, which are configurable in terms of what addresses they accept mail for and where they place the mail. Twisted also provides full SMTP and eSMTP server applications, which can easily be run from the command line using the Twisty utility. And now we'll circle back to Twisted's batteries included approach. Twisted provides an infrastructure for building applications, and Twisty is a cross-platform utility for deploying them. It handles starting and stopping applications and supports logging and daemonization. As we saw, Twisted provides application versions of servers for most of the protocols it includes. Here's the Twisty command, which will start an SMTP server, which accepts the mail we sent with our single message client. It runs on port 8025 and accepts mail for the user named recipient on the example.com domain. It stores the mail under /temp/example.com. So, we talked about how Twisted provides building blocks for creating network applications and why the event-driven approach works well for them. Then we talked about the basic abstractions that Twisted uses. The reactor and deferreds make it possible for Twisted to take an event-driven approach. And transport protocols and protocol factories are the basis of all of Twisted's networking. Twisted provides low-level APIs which allow access to the stream of bytes over the transport layer while hiding the gory details of sockets and other operating system functions. And Twisted provides high-level APIs which make it easy to write clients and servers for standard protocols. And if that weren't enough, Twisted comes batteries included, with working clients and servers implementing many of the standard protocols which can be run right from the command line using the Twisty utility. Twisted provides a lot of functionality. I've only scratched the surface, but the abstractions that we've discussed run throughout Twisted. If you'd like to learn more, I can recommend some great resources: an online tutorial, a book, and the Twisted website, which includes examples, tutorials, and a lot of documentation. Now I have a few minutes for some questions. What am I using Twisted for? I started out I wrote a BitTorrent client, and initially I wrote the event loop in straight Python, and then I converted it over to use Twisted. And I also wrote an IRC server just as a project, and I used Twisted for the basic networking. It takes care of a lot of the edge cases and the stuff where if you were writing it yourself, you'd eventually run into problems and have to fix them. Twisted is much more robust.
I use Tornado for asynchronous web programming.
I don't have any experience with Tornado. Sorry. But is Tornado just a web server?
I think so.
Okay, so Twisted is a lot more general purpose. You can use Twisted anywhere from just taking care of the socket connections and writing your own protocol for talking to another computer to all these other standard protocols besides web access. The other thing I did in my BitTorrent client was I also had the same program running a web server, which I used to, and I wrote a very little JavaScript front end to control it, to tell it when to start a torrent and giving feedback on how much had come back. And Twisted has a really great piece of it where you can very easily define your own protocols, and that's what I did. And so just a very little bit of code translated into a lot of functionality.
Hi, thanks. I'd be curious to know what companies use Twisted in production and what are the primary applications?
I know that a company called Zulip, which just got acquired by Dropbox, and I think Dropbox may also use Twisted. And I know that they do their mail stuff with it. Off the top of my head, I don't know other companies, but I do know that Twisted's used in a lot of projects.
So ideally, would this be used primarily for prototyping? Because you've mentioned that it could also perform some of the native services like FTP. So from my perspective, why would I want to redo something like FTP and Twisted when my OS would perfectly provide FTP services without it? So if I had a custom protocol, I see that this does have a lot of potential, but for a lot of the basic services, why?
Well, one reason you might want to do this is if you want to have one program with multiple network things going on at the same time. Like in my example with my BitTorrent client, I was doing the BitTorrent protocol using Twisted, and I was also running a web server with Twisted. And by doing it with Twisted, you can run all these applications as part of the same program and share data very, very easily. So that might be a reason.
Hi. Almost alone among the major tools for Python, Twisted doesn't support Python 3. Do you have any idea what the reason for that is? I mean, is there some... What reason do you suppose it is?
I think you might know more about this than I do.
No. I have no idea.
I'm not sure. I think there is an effort underway to convert to Python 3, but it's not there yet. But I think it's in process.